In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice? A flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of sound.
All right, hello and welcome, lads and ladettes, to Celestial Theodolite update number 36. Last week we made some awesome progress, got some great answers to some questions. If you haven't seen that clip, it was, here's a link to it. You can go here, watch the conversation with Jesse and I. It was actually pretty productive. And then down here in the comments, a brief summary was left of it and the response of that as well. So if anyone wants to read the summary from last week, this is an excellent recap, or way to get the recap. A big part of the contentions last week was simply that the celestial theodolite analysis is strawmanning the globe. In other words, comparing where the geometric intersection missed compared to where they predicted it would be versus where it occurred for flat Earth. Apparently this is a straw man of the globe. So I went through and came up with a series of questions that are about the globe model that we could follow along and answer. And, and if they're not true, or if you disagree or are unsure, you could ask for clarification on them. But all 15 of these, I think by the time we get to the end of them, you won't say that we're straw manning the globe in any way. So I asked for some volunteers earlier, but there seems to be not many globe lads on tonight. So Coco generously volunteered her time. So she's going to be our stand-in glober. If any chivalrous globe lads would like to step in on her behalf and answer as well. Chivalrous. Thank you, sir. That would be awesome. But otherwise, Coco, whenever you are ready, my lady.
I guess I'm ready.
Awesome. Fantastic. So some of these are written in kind of technical terms or whatever, but I'll break it down to, what it is. So question 1, do you agree that that on a globe, the geocentric position of a star relative to an observer is said to move at 60 nautical miles per degree and at a time that corresponds to sidereal time, so a little bit faster than 15 degrees per hour, and then plus or minus latitude variation. So depending on what latitude, it's not quite going to be at that sidereal time.
Oh, Alan, I'm not going to do anybody justice. It sounds familiar, so yeah. I would want to say yes.
Yeah, so basically
I don't know if that's true or not.
Yeah, so we can go into it and kind of explain it and break down like why it's asserted in the globe model and whatnot. So have you ever heard how they'll say that the positions of the stars change as you move across the surface of Earth, and like the rate at which they change is like a fixed rate?
Yeah.
Yeah. So
well, I mean, plus they're moving themselves a little bit at a time. Yeah.
Yeah, but for the purposes of like, navigation and like where's the star at right now, like they have it down where based on this time and this distance amount, they know how the angular change is going to respond. Does that sound fair?
Okay.
That's basically what that's supposed to represent. Awesome. Okay. Question number, and then quick clarification for the lads and ladettes at home. The geocentric position of the star is the true position of the star. So that's the position that follows this asserted linear rate. The apparent position is assumed to be affected by varying levels of astronomical refraction, and that deviates from that true position, but the true position is based upon that geocentric position. So they have like a way to analyze the star, like where it should be with respect to where you actually see it. Okay. So question 2, do you agree that to use the celestial sphere and the terrestrial sphere models 1-to-1, you need to perform a topocentric to geocentric transformation. Now that sounds like a lot of scary stuff, but all that is that's talking about how when you sight a star at an angle, you need to figure out how much refraction corresponds to that angle so that when you subtract it, you get the geocentric position of the star. And the geocentric position of the star is that angular position of where it would be on a globe of the radius of 3959. And so that's all that means. We've read
Oh,
about that in
I
yeah, you're
was
good.
gonna ask Wesley if I agreed with that or not, and he left.
Well, we could pull it up from a celestial navigation manual. So this is a short guide to celestial navigation from Umland. We've read from this before here, but excuse me. So here we go. So calculations of celestial navigation always refer to the geocentric altitude of a celestial body, the altitude measured by a fictitious observer being on the plane of the celestial horizon at the center of Earth, which coincides to the center of the celestial sphere. So, in other words, if you're up here making an observation at some angle and you know how much refraction it is, and you subtract that out, that gives you the angle that it would be as if you were an observer at the center of Earth, and that light ray coming from that star had like no refraction between you and the star, and it just came directly to your eye. That's the angle that that star would be at for the fictitious observer at the center. So that's all that means.
Okay.
All right. So, question 3. Do you agree that the geographic position of the star is defined by a light ray emitted by the geometric position of the star? This should be geocentric position because it's anyway, to keep the terminology consistent, but these mean the same thing. Of the star intersecting with the observer's eye at the center of the terrestrial sphere using a radius of 3959. So that's just kind of like, these two questions here kind of go hand in hand, 2 and 3. But again, that's just what we just read here is exactly that.
Yeah, that sounds about right. Yeah.
All right. Thank you, Coco. Okay. So let's see here. So, do you agree that to make an eclipse prediction, the geocentric position of the celestial bodies intersecting or how they align, when they form a conjunction rather, and also for occultations are predicted using the geometric intersections, not the apparent? And if you don't know the answer to that one, that's okay. We can pull up some stuff.
Yes, I don't know the answer to that.
Okay. No problem. So we will go to South Theo Prezzies? No. Oh, I didn't publish it. Okay. That's fine. Okay, so if we go down here to actually, let me just publish this real quick. It'll probably be easier. Give me 1 second. We can look at these more. Actually, I can just pull them up from here. Okay, so let's see here. We were talking about occultations earlier. So this is a reference where the French were using occlusions to measure the difference between local solar time and sidereal time. So, you know how there's a slight difference between the two? Well, back in the day, they didn't have, easy digital clocks or things to keep track of that stuff automatically. So you could use the sun during the day to tell your local solar time, with respect to solar noon for you. And then once you have that, you can take some occlusion measurements and measure the timing between them, and that difference will give you sidereal time. So that's one example of using the true positions of the stars. What they say here is that at high zenith distances where there's not that much refraction, like when the angle is like close to 90 degrees. So actually, I think it goes all the way down to about 20 degrees. So from 90 degrees above your head to 20 degrees to the horizon, they say, like, you don't have to account for that much refraction, or you can just ignore it essentially. And so when they watch the occlusion, they mark that time and they don't worry about the refraction. And then when they get closer to the horizon, they say you have to account for refraction, and by account for refraction, that of course remains subtracting it so that you know where the geocentric position is, and that's what they're doing. So that's one instance, and then another instance is uh, if you go to nasa.gov here, I'll put the link here. They attribute all their eclipse predictions to a guy named Fred Espernak, who's known as Mr. Eclipse. And what this guy did is he gathered a bunch of uh, data tables from other civilizations and other countries and whatnot, and used the geocentric positions of the stars as the reference from those, and came up with, I'm sorry, not the stars, the sun and moon for eclipse cycles. He just basically took their data, which is all dependent on the intersections of the actual positions, not the apparent positions. And so he says here, the geocentric ephemeris for the sun and moon has various parameters, constants, and Besselian elements. And Besselian elements is another where they look at things from that geocentric fictitious Earth observer position. So all of these are corresponding to them using the geometric position. This is a book from Carol Dale, who says uh, occultations and observation methods. So basically, how to make eclipse predictions. And what they say here, so to predict the time of occultation, the geocentric coordinates for the observation point are first computed. The right ascension and declination of the moon can be found from the ephemeris, yada yada. But the important part here is that the geocentric coordinates are referring to that unrefracted position, that position that follows their idealized spot and all that. So, this is them using the true geometric positions for those. And I think that's all I got on that one. There might be a couple other ones. Let me see here. I think I have a few other ones. Let's see here. The apparent position. That's not related to occlusions specifically. Yeah, when they talk about predicting where the shadow is going to be within their coordinate system, they're all, they're using the geocentric position there. Let's see. Reductions to the center of the Earth. The place of the stars is given by the ephemeris to those which are at the center of Earth. They are called the geocentric or true places. So yeah, it's basically, oh, and here they define a solar eclipse as an occultation. So again, what we're seeing here is a pattern of using this fictitious observer at the center of Earth to make the comparison. So after seeing that, like, I mean, I wouldn't, I it's, it would be hard to say that it would be a straw man, or or it would be hard to disagree with this. So, but did any of that make sense or track for you, Coco?
Yeah, mostly.
Yeah, cool. All right. So basically, like, they have this reference point that they need to compare it to, and it's this idealized geometric position that they're calling the geocentric position, which is referencing where it would be for an observer at the center of a ball, and then like what angle would that light ray intersect with the curvature at to define its true position. And then same situation for predicting eclipses and whatnot, like how they're going to be viewed for the observer. It's all going to all be dependent on where they see the geometric intersection at. Let's see here. Oh, and even in that one, I think, one second. What's that one at? Yeah, they make no, like, they don't deal with refraction in that. Okay. Um, so question 6 then. Or no, that was question 4. So question 5. Do you agree that the angle we measure to the star is reference to the observer's local horizon, which is defined as the horizon coordinate system? And the horizon coordinate system is a technical term from celestial navigation which we can reference here. The horizon system of coordinates, and like you can look this up on Wiki. It's basically taking the the sensible horizon, that would be like the horizon that you would see if you had a line going right out from your eye all the way to where the ground meets the sky. And then the geodal horizon would be if there was no refraction and there was just geometric ball curve there, that would be where the ground meets the sky. And then the celestial horizon would be like, so suppose you were standing on the north pole of the ball, and the celestial horizon would be like you could think of it like the equator, but just extending out into space from there. So all of these are related by when you make an observation and you remove refraction, that puts you down here in this position where you're referencing the angles that would be seen from here. Uh, and that's all that means. That's just how they define the horizon, as these 3 points all converging optically, but they remain parallel to one another. So these 3 planes are parallel to each other, although they optically converge. So basically, it's just kind of like a definition. Like, do you agree with how you would how to interpret the sky from an observer on the ground? It's defined as the horizon system of coordinates. And Pale Rider, you're hot micing a little bit there. Thank you, sir. All right. So Coco, what do you think about that one? Pretty solid on the definition.
I mean, unless somebody else disagrees, how you explained it and everything makes
Yeah.
sense to me.
I'm sure that if I
Yeah.
egregiously misrepresent it, somebody will step in to correct me immediately. There's enough gold
That's
lads
what
here
I
now.
figured.
So yeah, they're letting you take the fall for it because they're not quite sure where it's gonna go yet. But they're if there was actually any
I'm
disagreement,
I'm
they would.
happy to agree if it yeah,
Yeah,
I'm
you're
happy to agree if it makes sense.
yes, you're awesome. You're doing great. All right, question numero 6. Do you agree that on a sphere, any surface distance can be expressed as a central angle using the sphere's radius, and that half of that central angle equals the drop over distance between the 2 points that are subtending the sphere, which creates the central angle in the first place? So that's a little technical here, but let me bring up a diagram and then we'll walk through it. And it's a trigonometry thing that's that's true no matter what the model is or whatever. This is just an independent thing that exists as a function of trigonometry and geometry. So let's see here. Notes, trig notes. Okay. So basically, we have a circle here, which could be, and this also applies for a spheres. It's central angle theorem for both. But in this scenario here, just so we can get a visual of it, we take a slice of this pie. In this slice, these green lines here represent the central angle. So in this case, the central angle would be 27 arc minutes of an angle with respect to the center of the sphere or the circle here. And then this arc length that goes across here is actually proportional to some distance, which you can convert by multiplying out the radius, or you can divide by the distance by the radius to get the angle. So in any case, the it's basically just saying like there's a geometric relationship to distance on a sphere or on a circle, and then as a consequence of that geometry, half of that angle also represents the drop over distance for that entire arc length. So, for example, for Pikes Peak, we have an arc length of 50. Oops, let me put that on Pikes. Yeah. We have an arc length of 50 kilometers, which translates into 27 arc minutes, which is down here. And you can get that from doing radius times distance, and that will give you the angle there. Actually, I think that gives you the distance in meters. Dividing it gives you the angle. But in any case, that's what it comes out to. And then to kind of show that relationship even further, what you could do is you could say, hey, there's a mountain peak over here that's 50 kilometers away. How much lower is that elevation going to be because the Earth is a globe versus a plane? Well, you could take the rise over run to the peak and then just subtract half of the central angle from it, and that's always going to be geometrically what the angle should be for a globe. But that's that's an additional step that's not part of this question, but it's just showing that geometric relationship between the arc length and the half of the arc length, essentially.
Can I interrupt?
Absolutely.
All right, right. So the central angle is the rotation of the horizontal between the two locations. So if you have an observer at that topmost point on the circle and an observer at that angle position at where the X angle is marked, right? The central angle gamma represents the rotation of the horizontal between those observers. So if there's a star that makes an angle at that point where the mouse is, the topmost point of the circle, out there, the topmost point on the circle there. If there's a star that makes a certain angle at that point, if you want to find the angle the star makes at the point marked X, you can move your mouse. Right. If you want to find the angle made by the star over there, that difference in angle is equal to the central angle. That's a geometrical fact. What I do see in some of the calculations that great. So for example, if the angle is degrees at the topmost location, the angle where the mouse is right now would be 3 degrees minus 27 arc minutes for that Pikes Peak location. Agree with that?
Say that again.
So if the angle at the top of the circle was 3 degrees, the angle where the mouse is right now should be 3 degrees minus gamma, or 3 degrees minus 27 arc minutes.
Yes.
All right. Because what I've seen in some calculations that I've been presented is you're subtracting gamma over 2 and not gamma. So I just want to point that out.
Subtracting gamma over 2 and not gamma. When referencing the
Correct.
positions of the stars, we're always referencing the central angle. When referencing mountain elevations, we're referencing the half central angle for the drop over distance. And then when we compare the difference between the two, we're always off by the half, or like there's always a shared difference between us that is the total amount of the half central angle, which geometrically makes sense because we're both sharing the same arc length. But yeah, we never use gamma or half gamma on the stars. That wouldn't make sense.
Okay.
All right. But yeah, so question 6, though, I think we're both in agreement there. That is the geometric relationship between the arc length and the gamma, 100%. All right, so question 7, and feel free if you want to step in for Coco and take this or whatever. But do you agree that the horizon system of coordinates, do you agree that in the horizon system of coordinates, a celestial body with a negative altitude is geometrically below the observer's local horizon? Conceptually, this has a physical implication of the geometric curvature of Earth blocking your line of sight to the star, right? Similarly to how, like, when the sun is setting, it gets to negative coordinates at that celestial horizon. Oops, 1 second. It's setting below this, but it's, they say it's refracted up, so there's going to be, you see the delay. But when they're referencing this intersection threshold, crosshold, that's their baseline for when it should be, when the sun should start setting, when it should be blocked, right? And then deviations from that are refraction based. Does anyone disagree? Coco, I just need your signature right here, please. Since
Sure, Alan, whatever you need. That's
Thank you.
fine.
Thank you. All right, we're almost done. It's going to be painless, guys. Question numeros 8. We've made it this far, and we haven't reached any major
Woo!
disagreements. There was some clarification on 6, but so far we're 8 questions deep and no like serious contentions yet. Okay. Do you agree that a celestial body becomes geometrically set when the line of sight from the observer intersects the Earth? Now, obviously, the globe lads would say, well, there's refraction, so it's going to deviate from that. But as a general rule of what they're trying to represent here with all of this, that's technically when you should start the clock for it, right? Like it should have been set here when it's intersected with the celestial horizon.
Well, I mean, sure, I guess. Like, it's not because you're not saying that that can't change. It's just that for that particular moment in time when you're measuring it, sure.
Yeah, it's just setting it to like this is where it should occlude, and then deviations from that are, who knows, right? But that's the baseline for what or how they would even start to apply a deviation. Like deviation from what? Like obviously you need a baseline. Okay, so question numeros 9. Do you agree that astronomical refraction is defined as the difference between the geometric position of a celestial body and its observed position? So there we've given a really easy explanation for astronomical refraction. And this, of course, would
Um,
be. Go ahead.
I'm just gonna agree to that because I'm still trying to get this astronomical refractions stuff down.
Yeah. Oh, no worries. So when you're looking up at the horizon, or I'm sorry, when you're looking up at, like, say you're just looking out at the horizon, right? And then you look straight up 90 degrees. So you're just looking straight up at the sky. They say that when you're looking up, straight up, there's almost no refraction between the apparent position that you see and that geocentric position that they reference at the center of the Earth. And then as it gets down 10 degrees from that 90, so when you're looking at it at 80 degrees, there's a little tiny bit of refraction, but it's still pretty much indistinguishable. And then at 70 degrees, they say there's a little more. And then as you get lower and lower, every 10 degrees has their own kind of amount of or specified amount of deviation. And then as you get down to about 15 degrees, that's where that's where you start to have like quote unquote, a lot of refraction where the effect, starts to be something that you have to consider.
Okay,
So
so you're talking as it gets closer to the actual horizon.
yeah, well,
Okay.
just in general too, because it's not just that. Like the globe lads would never say that you see the true position 1 to 1. It's always going to be refracted, but the amount of refraction is dependent on the elevation that you're looking at it through. Because basically, they would be saying that at a lower angle, you're looking through more atmosphere, so that's going to be more refracted.
Okay.
Cool. Question
Can I
number.
add something?
Yeah, go ahead.
So that's correct. And the reason the refraction depends on the elevation angle is because as you get lower and lower, as you get closer and closer to the horizon, you're going through more and more atmosphere to see that object, or rather, the light from that object is having to go through more and more atmosphere to get to you. When the object is overhead, uh, it goes through a very minimal amount of atmosphere, whereas when the object is at the horizon, the light goes through much more of the atmosphere.
Well said. All right. Question 10. If the geometric setting of a celestial body is determined by the line of sight intersecting with Earth's surface, would the same geometric method of comparing intersections apply to predicting when the celestial line of sight intersects with a mountain peak? And that should say celestial body, the celestial body's line of sight. So basically, when a star intersects with a mountain peak, because for the globe, when they want to predict the sunset, they use, oh well, now it's at negative coordinates, it's below this geometric obstruction known as the curvature of Earth, so that's going to be our baseline for that. And so could we use a mountain peak that's at the horizon, that's at the observer's horizon, to calculate uh, geometric intersection predictions?
Okay.
So they're basically the same thing, right? One's just further away and kind of conceptual. And the other one is an object that you could at least see. But other than that, there's the same, I think.
Well, I mean, yeah, right? Because it's just the difference of if there's mountains around where you are and you're using that as a point, or you're in a desert and using that as a point.
Well said. Like, yeah, if you have a
Except when there is, sorry, I say something?
go ahead.
Except when there's refraction, because refraction bends the light from the object. So light coming from the object gets bent as it passes through successive layers of the atmosphere. So it's no longer an exact straight line. And that has been measured. We know that light, refraction can bend light. This has been measured for nitrogen and oxygen, the two major gases in the atmosphere, and I can share papers that have those measurements.
To be clear, the contention right now isn't does refraction exist or how does that affect the measurement? It's if they make the geometric prediction for when it should set, right? They're using a geometric intersection with a known terrestrial feature, the curvature of Earth with respect to the equator relative to the observer. So there's no difference in comparing those intersections also with a mountain peak at the observer's horizon. Right?
Are you saying that predictions of sunrise, sunset, and so forth don't consider refraction?
Nope, it's not what I'm saying at all. I'm saying that the baseline to know how much refraction is needed to apply, you need a geometric obstruction to start the setting process. And that's defined as the celestial equator, which happens to intersect with the terrestrial equator. So conceptually, what they're saying is that when the sun is setting, it is now going into negative coordinates with respect to the celestial horizon, and it's being geometrically obscured by the curvature of Earth, right? Irrespective
Correct.
of whatever refraction is going on, that's the baseline for what is starting the event of the sun setting. Then deviations from, of course, you guys would say astronomical refraction. Now, just looking at the geometric aspect of the sun setting and how it's predicted, right? Is there any issue with using a mountain peak to, using that same baseline? Like, hey, the globe says the peak is here, flat Earth says the peak is here. We're going to compare geometric intersections at the time of setting. Is there, like, it's the same exact scenario? So when you would compare the sunset on a globe, it would be, you would go, oh look, it's at negative 35 arc minutes or whatever it would be. I think that's like the typical norm or whatever it is for it. So that would be, you would confirm it through that, but you have that intersection baseline threshold that has to be crossed. Same exact thing that we're doing, but just using a mountain peak.
One factor that would confound this would be that the distance between the observer and the mountain peak would be different from the distance between the observer and the quote unquote end of the atmosphere from where the light begins to come. So light will have to go through a certain amount of atmosphere between comes from and the mountain peak, and between the mountain peak and the observer, and the refraction calculation would have to take that into account. And when things are closer to the horizon, that should make a difference. I have not done the calculation myself, but I'm pointing out that could potentially confound the calculation.
So again, though, we're not talking about post measurement corrections or like what would possibly change the timing. We're saying this is the baseline for what they're using for an intersection, and we're also going to compare the geometric intersections. There's no difference in our methodology as to what we're doing versus there's no difference for what we're doing with respect to how we're predicting for the globe versus what the globe would predict for any other astronomical event so far, right?
I see. But you're also assuming that the body has the same elevation angle at the mountain peak and the observer, which is not true for a globe.
No, we're not.
On a flat Earth.
Hold on a second. We're not assuming that that comes out after we after we go and see where the position was with respect to the peak at the time of occlusion. Because on a globe, it would have occurred earlier. So if you add the arc length back to go to the peak, the star would be at roughly 13 arc minutes above the peak for the true position. It wouldn't geometrically align for the observer on a flat Earth if the Earth was a globe. The positions would be reversed. But let's try and stick to just the methodology of what the globe predicts and how we're treating the globe for geometric intersections. So question 10, we're in agreement that comparing geometric intersections of the true positions is the baseline of how to start a prediction before you have deviations from said prediction, right? Like that's just true no matter what model.
Not necessarily. I disagree with that because on the globe, the body would set earlier or later at the peak than at the observer. Right? Where do you account for that?
The observer,
Right? On the globe, the sunset would happen. Sorry, after you.
well, that would be because you're going higher in elevation, but there's a difference here.
Not elevation, not just elevation, but there's curvature between the observer and the peak,
So-
right? So for example,
So
if the peak is 50 kilometers, yeah, go ahead.
yeah, so this is segueing back into the issue that we were talking about earlier, where at the time of occlusion, when you add the arc length back, it should be above what we predict because it would have occluded earlier before it lined up to the peak. Like when I go into the spreadsheet here and I adjust or I go to the test Pikes peak for the ideal globe, you'll see that the half gamma difference between us switches. It goes to what we're slightly off by that amount. So if you go into Stellarium, which I have over here, or yeah, why the globe predicts an earlier time. So if you go here and you add, if you were to go into Stellarium at this time, 184204, the star's true position for the observer would be at this location. And then if you went to the mountain peak at this time, the star is going to be 13 arc minutes above the rise over run to the peak. It's not going to work out because the Earth would have been like the asserted relationship of the stars, like that 1-to-1 relationship that we talked about earlier, would have led to the occlusion for the observer. That's when it would have intersected. So these differences would be reversed. So the only reason adding the arc length back makes it flat is because when it finally got occluded, it was actually geometrically aligned with the peak for the observer rather than the observer-centric prediction. But we can get to that towards the end here. We're almost done and we're kind of contending a separate issue.
So why don't we circle back to that later?
Okay. Yes, absolutely. So again, coming back to 10, globe predicts intersections at the celestial horizon using the terrestrial feature of the entire Earth as curvature, and we're using a mountain peak. So there's no difference in what we're doing for the geometric comparisons of when the event should start, not getting into how refraction may or may not change the timing. But there's no straw man here. Agree? Because you said earlier that it wouldn't necessarily be true when predicting a sunset or whatever, but it's always true because there always has to be some physical obstruction baseline for there to be a deviation from. So there's no scenario where the sun sets with respect to no geometric baseline comparison. Otherwise, what's it refracting from? Like, what is the 35 arc minutes of refraction with respect to, right? The celestial horizon, that geometric point. So there's no difference in what we're doing here. It's okay to just agree. Like it's just a fact. Just
Not when I don't want to agree.
well, if you don't want to agree, then why? Do you have a reason as to how? So so when any celestial object is occluded and set, there's its true position is in negative coordinates, and its apparent position is in positive coordinates, or it'll be at zero because it's set. Um, what is the amount of refraction deviating from? Some physical obstruction, right? So in this scenario where there's a mountain peak is the physical
I'd
obstruction,
need to see a
what's
diagram of
difference?
this drawn out.
Here's a diagram.
Do you have a diagram that I can refer to?
Yeah,
All
sure.
right.
And Shane,
So
if
the
you're there,
observer is at 90
yeah,
degree position.
yeah,
All right.
yeah, yep. Looking out at the horizon, there's a mountain that's tipped away by half gamma here, and there's a star intersecting with that point for its true position relative to the observer. That's it. Same situation where if the observer was here and you were trying to predict when the sun is setting, you would have it, the angle would be down here or whatever because it's going to be at the celestial horizon. But there's no difference in what we're doing versus what the globe predicts for anything. And Shane, if you're there, do you have that?
So what angle would stellarium give you at the observer? What angle does stellarium give you at the observer? And what angle does stellarium give you at the mountain peak?
So in this
Hey, Alan.
scenario, yeah,
Alan, I didn't mean to cut you off. Can I just extend my guy an olive branch here? Like,
sure.
just a
Where-
real quick one? Because, like, how many weeks have we been into the celestial theodolite? We're on, like, what, 48, 106? How many weeks has it been?
72.
72 weeks. Okay, so my guy, Earthly Skeptic, if you go back and listen on Alan's channel, Ether Cosmology, every single week they have been going over what this actually is. So that way we're not backtracking and we can let Alan go on with his presentation and his questions and things. All of your questions can be answered if you just go back and listen to any one of those number of episodes. There's 72 of them, just so you can fully digest what's going on. That way, he's not having to rehash like 101 stuff that he's been presenting from the beginning. Maybe I'm being a dick here, but
Yeah, I would
Yeah,
like.
also kind of
Yeah,
want
being
to
a dick.
continue with it.
yeah, I would like. I
You're
would like.
being
to-
a
That's fine
dick.
with me. That's fine with me.
Yeah, 1 second. So
That's
before we
fine
get-
with me. I just
second.
don't want to.
Before we,
I
get
just
off
don't want to
topic
give an
here-
answer in that case because
Yeah, before we get off topic here, this is pretty dense, and especially if it's not familiar, it's so it's fine going over it repeatedly and stuff. And like he specifically asked for a diagram or whatever, so it's fine. And then in regards to
All right. My apologies.
yeah, no worries. He's in, and then to
all right. So
to
Alan, do you want to
and-
discuss this for a few minutes then?
Yeah, real quick, I got the position of the star for you. Just give me 1 second, and then I just wanted to add on to
Right.
this gentleman's credit. He's doing his own presentation on the celestial theodolite data and his interpretation thereof after our presentation. So he's put in quite a bit of his own effort into understanding it, or like trying to deal with it or whatnot. So shout out to him for doing that. Now, the answer to your question, observer location, they say that the star is at 206 true position, and when added back to the peak, it comes out to be 233, I think it is, off the top of the dome.
Mhm.
Yeah. So look, this is what was measured.
Or they're
233.
not right. Yes.
Yep. Now, real quick, take a look at, remember what I said earlier about how if it occluded closer to what the globe geometry predicts for the observer-based prediction, look what happens to the position at the peak. So instead of being 233, it's going to be 244, I think. Yeah, because you're basically adding 13 arc minutes to it because it wasn't able to get to that elevation with respect to the peak because it would have already occluded at that geometric time, irrespective of how refraction may or may not have changed it. This is what would have happened, if the occlusion, happened earlier, this is what it would look like. So like if refraction affected it some, there would be some discrepancy, but on both sides, but we would share the larger portion of the air. And when you add the arc length back between us, they would not intersect, making a congruent triangle from the rise over run to the peak to the peak. I mean, I'm sorry, to the star. So, okay. And then you had a question, or did I answer it?
Not quite, but you're saying that there's no refraction if the object is at the line of sight from the observer to the peak. If the star is at the line of sight from the observer to the peak, then the next instant the star should disappear, correct, for the observer.
Mm-hmm. Yep.
Let's say at one instant of time, the star is exactly at the line of sight between the observer and the peak, and there's
Yep.
no refraction. Then at the next instant, at the next microsecond or whatever, the star should disappear.
The next second, because they, about 1 second corresponds to.
It's frames, and you're doing 1 per second, correct? That's fine, but then you still have refraction. Refraction is a geometrical, physical phenomenon, and you can't divorce that from what's happening. So, in that hypothetical, imaginary scenario, yes, but in a realistic scenario where refraction takes place, no.
Listen, real quick, like, you're trying to argue in a point that isn't there, right? No matter what,
It is there. Refraction is there.
Before you have to know how much refraction it's deviated from, you need a geometric intersection baseline to compare it to, right? That's all the question is. That's all you have to agree to. You don't have to agree that there's no refraction or anything like that. This is just setting the tone for how celestial events are predicted through the geometric intersection, whether it be a terrestrial feature or celestial bodies occluding themselves, or occluding, one another, sorry.
Right. In an imaginary scenario where there's no refraction, yes, you can predict it that way. But when there is refraction, it's going to alter the time.
So you say an imaginary.
I don't think you're very satisfied with the answer.
Well, because you're trying to say it like it's a different thing, or like incorrect. Like you're like an imaginary scenario. Well, how about a real world scenario like an eclipse? How about a conjunction? How about an occlusion to determine the difference between sidereal time and solar time? All the stuff that we just went over. Like at this point, you're now saying that no geometric intersection is required, and you're trying to make it about refraction. It's not about that. It's about, we're comparing a geometric intersection just as the baseline for what we're doing, right? We're not considering refraction. We're not saying it doesn't exist, but just as a baseline for when the occlusion should have happened, it would be for the observer when that star's true position is lined up with the peak, right?
If there is no refraction.
Right. So there's no issue in comparing geometric intersections with a mountain peak, or
if there is no refraction.
Even if there is refraction, you still need the baseline to even start the comparison. So you can't be like, it's not a different thing. You're going to add refraction to what was missed, right? So you still need that event to occur or not occur, but you need that baseline for there to be a deviation from it. That's all this is. It's as simple as that. So I think we're in agreement.
All right, if it's a baseline with a refraction, then that's fine.
Nice. Perfect. All right. Question numeros 11. Do you agree that mountains are part of the surface and therefore part of the same terrestrial sphere as the geometric setting predictions, which we already went over, or these are kind of one and the same. So we went over the example of the sun setting with, being below the celestial horizon coordinates that equals a negative angle, which means that it's, physically obstructed by the amount of ball curve between you and the celestial body. So I think we're all in agreement on how that works. And then obviously a mountain peak is part of that. So there's no reason as to why that wouldn't work. Do you agree?
Let Coco handle this.
I mean, just assuming that, no refraction, you can always refract later, right? But geometric baseline comparison, this is where we're at, right? Observer makes the observer-centric prediction for the globe. They compare it to where an observer would see it on in the center. If there was no refraction, you would take your baseline from that, and then your deviations from that would be refracted, right? So there's no, I'm not strawmanning the globe, because how are you going to get it to your refracted position to correct for if you don't know where the intersection was missed at? Like, obviously this is true regardless. And forcing it on Coco is kind of, what's the word for dishonorable? Anyway.
Oh, come on. Coco was answering all
No,
the
no,
questions.
no.
I stepped in twice.
because you
Don't
know
tell me
it.
I'm forcing it on her.
No, well, this is true. We already agreed to this. This is just,
We
you're like,
agreed to that if there were no refraction, which is an
Right.
imaginary scenario. Continue.
which is what all globe-based predictions for celestial interactions are based upon.
But they do incorporate refraction. If you look up sunset and sunrise times, they will account for that refraction because the sun is visible 2 minutes earlier before some number of seconds earlier before sunrise and a number of seconds or minutes after sunset. And that is accounted for in the timings.
No one here is saying that you can't make
You cannot
a secondary correction after the fact to make it match what's observed. We're talking about geometric baselines for there to even be an amount to add for there to be that amount of refraction. Otherwise, what's the
I said
amount of,
if there's no
then
refraction, then it's right.
correct. So you agree with this one as well, which was that the mountain peak is part of the same thing. So what we're doing is just as valid for comparing those intersections.
I was not paying attention to it. That's why I asked Coco to go ahead.
Gotcha. All right. So do you agree that the central angle corresponds to an equal angular displacement of the celestial sphere 1-to-1 due to the celestial and terrestrial sphere relationship? And that's something that we went over earlier. So the arc length being 27 arc minutes, that's also going to correspond to how much the drop in the sky is as the star traverses that amount of ground distance. So I think we're all in agreement there on that relationship.
Yep.
Question 13. Would this mean that the globe model makes a geometric prediction for the angle at which the star intersects a distant mountain peak? Now, obviously, this is before refraction because we need the baseline to compare it to. So, any disagreement or? I take silence as acquiescence and tacit agreement, because otherwise you would definitely correct me. But yeah, if you have if you're setting up your comparison for how much there's a deviation from, this is what it would be based on. Question 14. Do you agree that the difference between the spherical globe elevation angle and the planar elevation angle is half of the central angle between the observer and peak? And that's regarding mountain elevations. So we went over that earlier in the beginning, how you could subtract the half gamma from the rise over run to the peak to get what the globe predicts, or you could do it through spherical trig or a number of other ways. But in any case, you can take that angular amount over that arc length and convert it to what it would be in meters. So whether you want to look at it in terms of an angular amount or a meters amount, it's always going to be half of that central angle angularly.
Is this the mountain elevation or the star elevation?
Always the mountain elevation when dealing with half gamma.
All right.
All right. Question numerous 15. If yes to 14, then could we test whether curvature exists by comparing the measured mountain intersection angles to what would be predicted for the angle at the observer over that distance? The difference would be half of the central angle. And what we went over earlier when I showed, what was measured here, we have a deviation where the globe has all the curvature error. And then if we flip it to where it would have lined up with the globe, flat Earth ends up with all the curvature error, which is the half gamma which is the half of the central angle. So that, so basically, when we go to compare positions of the stars, when we add the arc length back, instead of referencing a fictitious observer at the center of the Earth, we're going to anchor it to that mountain peak and see, if it was lined up with the mountain peak. Because if it's lined up for the mountain peak, that would make a congruent triangle from light source to mountain to observer to be the more likely cause of the occlusion, because there's only one thing. Well, there's two possible things at the end of this arc length, at the end of this 50 kilometers here, and that's a mountain that has a drop over distance to it. So it's either going to be 217, or it's going to be the flat Earth rise over run to the peak at 231. So there's two possible things at the end of that arc length. Now, when the globe misses their timing, whenever the occlusion actually occurs, the deviation is split between us. So the closer the closer that the star is allowed to get to the elevation of the peak before it occludes, the flatter the Earth is, essentially. And then if to reverse that, if it occludes closer to what the globe predicts, then that deviation switches and we end up being off by what they would predict. So they become different. So that's the methodology. That's the whole process, right? For every star peak, that's what we do. We compare, instead of using the fictitious observer, because that's what the globe predicts at the center, we use the mountain peak to reference the geometric alignment. So that's all we're doing. And then the half gamma elevation difference ends up becoming the like, you can see the difference in the position of the star at the time of occlusion is also going to show that, like, that's what that relationship adds up to, that deviation, the drop over distance. So it's quite interconnected geometrically, and if the Earth were a globe, the errors would be reversed. But that's the whole method and what we're doing for comparisons. But in terms of strawmanning the globe, aside from not considering refraction for the post analysis, but just in terms of raw geometric intersections.
No, there's one more factor. Other than refraction, there's one more factor.
Mm-hmm.
Can I ask you a question?
Go ahead.
So you said it's rise over run. Could you give me the values of the rise, like the mountain elevation and the observer elevation for that? And Aquarii and Pikes Peak observation?
Yeah, the rise is going to be 20.
So the mountain Pikes Peak is 4,300 meters above sea level, and the observer is 2,073 meters above sea level.
Yep, that gives us a delta H
and
of 2227. Did you ask me to
Right.
give it, or did you say or did you ask me and then
I'm asking
me the values?
I'm asking you, and I'm reading it as I'm asking you, and I'm reading it as you're pointing that on the screen.
Yeah.
So the distance is 50,551 meters. In a previous presentation, you had 50.7 kilometers. That's 50,700. Could you tell me how you get that distance?
Yeah. So Jesse and Mike were having a comparison of like two different websites. One was using Haversign. The other one was using NOAA. So it uses like different things to get distances or whatever. What we ended up doing to just make it all uniform was just doing Haversign with respect to the latitude, longitude inputs. So all the distances on the spreadsheet now come from Haversign, and then the latitude and longitude of the peak and stuff respectively. So we just do it from that. And then we have air bars generated from a standard Gaussian distribution. So
I see. So you input the latitude, you input the coordinates of the observer and the coordinates of the peak. So the latitude, longitude, I guess the elevation doesn't matter for the rise. And you use Haversign with a certain radius to compute that distance. What was the radius used?
The radius used is 6,371,000 meters.
That's the radius of the globe, you know?
Mm-hmm. That is what they say. But that
Right.
radius is
So you're
also
using
one
using a
second.
form,
1 second.
right?
That radius is tied to a fictitious observer to linearize the positions of the stars, which we went over on the first question, or the first couple questions. This amount of
I was not paying attention there.
Oh yeah, so check this out.
I see.
Anyway,
The 60 nautical miles per degree
Mhm.
is tied to that radius. Now, 60 nautical miles per degree happens anywhere on the globe.
Well, it's derivable
You
entirely
don't have to
from
be at
one second. It's derivable entirely from positions of the sky. And again, to even use it for this, you have to use the fictitious observer at the center. Because you're using a fictitious observer at the center, it's not mutually exclusive. It's a conceptual model calculation.
Center of
So
which center? Center of the Earth?
for this, yes, to bind the celestial sphere to the terrestrial, you have to do that. It's an assumption made to put the fictitious
No, I can measure
observer
the
there.
pole star.
Yeah, it's derived from empirical
Okay.
observation. I don't disagree. You think it's the radius of Earth.
Yes,
I'm saying it can equally be the radius of the celestial sphere.
No, because the 60 nautical miles per degree, the degree is the celestial sphere. 60 nautical miles is the distance on the surface of the Earth. The 60 nautical miles is actually measured, and I've done the experiment myself. I was in Iowa where I had a perfectly straight north-south road. I measured the elevation of the pole star at one location. I drove 69 miles north. It went down by approximately 1.00 degrees. It went up by 1.00 degree, actually drove south. So that's a measurement you can do for any star anywhere on the globe. If the star is not the pole star, it's going to move. You need to have two observers 69 miles apart and or 60 nautical miles apart. You can have them measure. So that 69 miles per degree is measured by looking at the degree in the celestial sphere and comparing that to a distance on the Earth. That's applicable for any star anywhere on Earth. That property is a geometric property of a sphere.
I don't disagree with what you're saying, but here's the thing: the ground distance.
It's awesome. That means you confirmed the globe.
So
Thank you.
You can't interrupt me in the middle of when I'm about to talk to be like, look, it's globe, as I'm about to explain to you that the unit of measurements to traverse distances is a ratio of the coordinate system itself. So of course the angular displacement corresponding to that is going to be internally consistent. Just making the observation alone, you can derive Earth's radius. To use to compare where the stars should be and whatnot, you use that as a fictitious observer for that amount. It's not mutually exclusive, and I'm not disagreeing that you can't move 60 nautical miles across the Earth to get the stars to deviate. That's what I'm saying, is that it's an optical effect. You're saying that it's due to ground curvature. Now, what we did was do occlusions and compare intersection differences to see if it's the ground that's curving or if it's the sky that's curving. If the ground is curving, then those half gamma differences between our measurements for globe and flat Earth would be reversed, which is what we went over earlier. So using the radius value that comes out of that as a computed value, using the internally consistent system where a ratio of the change in the sky is a distance on the ground, you're not going to see any discrepancies. But when we compare the occlusion timings, this is where the geometry difference is revealed, because the air difference shows up for the globe instead of flat Earth, meaning that the predictions were closer to what flat Earth predicts. Now you have to take the position that there was just so happened to be the exact amount of refraction needed to cause that occlusion, and then even when you use those values, they don't often add up to the amount of gamma difference. There's almost no correlation. There's a couple times where it's close. Like actually, that's if you incorporate terrestrial refraction to the peak, which I disagree with on that being an occlusion. But geometric intersection wise, they're always above the peak. And then if you look at the terrestrial, sometimes they'll be aligned with it. There's a couple cases, but they're often still over the peak in that regard as well. So if your assertion of haha, you used globe, you confirmed globe because you internally referenced the coordinate system with respect to itself, and then that's not confirming the globe. When we externally test it, instead of anchoring the position to the center of the Earth and we anchor it to the mountain peak, we find out that the Earth isn't following the geometry that's prescribed by the globe, because if it was, then the flat Earth prediction would be off by Earth curve. There's a 13 arc. There's a 13 arc minute difference between these two. Go ahead.
All right. You know that Haversine is a formula applicable geometrically only to a sphere, right? You're computing the distance between 2 points on Earth. That formula is applicable only if the Earth is a sphere. You know that?
Well, The latitude and longitude coordinate system are spherical coordinate systems. That's what makes up the graticule. So when you're computing distances between those, you're using positions of the stars rather than computing anything or like measuring anything on the ground.
What
You're basically calculating
does
positions
latitude mean?
of where the stars
What does
are.
latitude mean?
Latitude is the angle of a star, and
How do you determine a place's
longitude
latitude?
is the time that the angle will be at that location. What?
All right. So suppose I'm in a new location. How do I determine the latitude and longitude of that location? Suppose I have an accurate clock with me that tells me the exact time or the exact time difference to Greenwich. How do I compute the latitude and longitude of that location?
Well, for latitude, you could just take the elevation to the pole star. That'll give you your lattie. And then for longitude, you'd have to reference another star. There's an angle at a specific time, and then look up where, or that corresponding angle, subtract the amount of refraction, and then do the what is it called? I got it over here. Is it the local hour angle, or is it the Greenwich mean angle? I forget. But
The
anyway,
Greenwich sidereal time
yeah,
and the
that's
local sidereal time, and you
yeah.
subtract them and you get the longitude.
Yep,
Right.
there you go.
What do you do in the southern hemisphere where the pole star is not visible? We all know the pole star is not
Ooh,
visible south of the
so
equator. What do you do there?
so what the Chinese did is they used the star Canopus, and they mapped out an exact 60 nautical mile per degree relationship with Canopus as they had with Polaris. And instead of using, a nautical mile, they used a Lee. So instead of a nautical mile, their ratio was to a Lee, or like, they didn't have meters. So they used a Lee. But anyway, when they got that ratio of Lees to the angular change of the star, they used that for their guiding pole star. And then there's two stars that lead the Southern Cross. I forget their names, but it's Gamma, or it's some Draconis or Crux or
Equinox
something
and
like
gamma
that.
clock.
Yep, those are the ones. They use those two to figure out
Draconis
where.
is different.
Oh, yeah, that's the one in the north. But anyway, you got the names. So they use those two to figure out where the celestial, what would it be, the true magnetic south pole, or whatever it would be, the celestial south pole. Anyway, they use that to point to. So that's how they did it back then.
I don't think it could be Canopus because Canopus is not visible in northern China. I don't know where they did this from, Beijing or Shanghai or wherever.
No, that was when they did
It
an
could not have been
expedition.
Canopus.
No, it was. They did an
I see.
expedition in the 1400s to go and map it
The
out
southern
specifically.
hemisphere?
Yeah.
I see.
They were actually the
Alright.
first people to go through the Magellan Strait. Shout out to the
I
Chinese.
see. I didn't know that part.
Yeah,
Right. Canopus is a southern hemisphere star.
correct. It is a southern circumpolar star. Its highest altitude is like 88 point something degrees, and its lowest is like 14.
That's believable. But the Haver-Sign formula applies only when the surface is a sphere, when the Earth is a sphere. I completely disagree that you can use the Haver-Sign for a flat Earth. For a flat Earth, the formula is different. And if you use that, you get a very different distance using the same latitude and longitude. So the latitude and longitude are measurable. We just went over that you can measure the pole star elevation and you can measure the hour angle of a star. So you can measure the latitude and longitude. You can define lat and long on the flat Earth disk. But if you do that using the same measurements, you're going to get a very different distance compared to 50.7 or 50.55 kilometers.
If you take
So you're using the wrong distance for your null hypothesis of flat Earth.
If you take a chord over that same arc length, like for Pikes Peak, for example, the difference
It's not the
14.
It's not the chord.
14 centimeters.
It's a different formula.
So
Hey,
I don't know.
listen. You gotta have to stop interrupting, bro. You
Yeah,
gotta let him flesh out his answer.
Well, if you have a different way to derive distances on flat Earth using a different coordinate system, I'm all ears. But for the purposes of using a spherical coordinate system, which that's what the latitude and longitude system are, it's an abstract coordinate system, it has nothing to do with the shape of the Earth. Now, it's asserted that that the stars, define those positions of the Earth because it's a sphere or whatever. But the computations within the system itself are based off of linearizing that 60 nautical mile per degree relationship and then using a fictitious observer to compare it to. So it's not mutually exclusive to any model. And I agree with everything you said about using the positions of the stars to derive the basically Earth's radius. We actually show that last week with with what Goose put forward in terms of explaining how you can derive the central angle from the arc in the sky. So we can get gamma and half gamma from the positions of the stars, right? If we subtract position of star true from position observer true, that's 27 arc minutes, my boy. Half of that arc minute, or half of that is just the half gamma. Now you can also derive that using, the radius value in meters and whatnot. But the point is the arc in the sky versus, curvature on the ground. This is the geometric implication, or like these measurements are the geometric result of there being no curvature on the ground, right? All this, everything that you cited is all math and coordinate systems that don't have to correspond to the shape of the earth to use them, because it's just a conceptual model with the fictitious observer that linearizes the movement of the stars to match the conceptual model. What I'm putting forward, right, with these measurements, what these imply is that if you were able to have an observer take a zenith measurement of this 39 Aquarii as it were getting occluded, for Mike 50 kilometers away. If you were on a globe at the same time, this star would be at a zenith position for someone that's I think we actually have the distance here somewhere. Was it ground distance, GP distance? So 9,700,000 and something thousand meters away. So that's where the ground position should be. I'm saying that if you were capable to have an observer there and look up, the position of that star would not be there, because this is bound to a calculative value that we all agree on, that you can certainly reference that as if it were true, but no one's actually verified that relationship, and the deviation in these occlusions show that the use of it is just a conceptual model agreed upon by everyone.
Can I talk?
Absolutely.
All right, thank you. The 60 nautical miles per degree has been verified. I've done the verification. Lots of people have done it. It's what sailors used. It's what celestial navigation uses. That requires the Earth's surface to be a sphere. No exceptions. If the Earth's surface is not a sphere or an approximate sphere, that relationship will not be valid. You said you're using an abstract coordinate system. The coordinate system is measured. You and I both agreed that the coordinate system can be measured. You can use Canopus in the southern hemisphere and Polaris in the northern hemisphere to measure the latitude, and you can use an accurate chronometer or watch to measure the time and the time difference to Greenwich and look at the hour angle. So that gives you the longitude, and both of those together would give you the coordinate, the coordinate of that point on the Earth. Once you have a measured coordinate system, you can put that on an azimuthal or flat Earth map. I've never seen a map or a model from the flat Earth, but if there is a model, then we can put it there. Depending on how the coordinate system is set up on that model, the distance formula will change. But I looked at a very standard distance formula. It's much easier to work out distances on flat planes than it is to work out on a sphere. On a flat plane, you'll have one formula. On a sphere, you'll have the Haver sign. The Haver sign is, without exception, a formula for distances between 2 points on a sphere. If the object is not a sphere, Haver sign does not apply. So I disagree with the first point, your first question, which I was not paying attention to when you first mentioned it. And I disagree with the last question, because the last question for your null hypothesis uses 50.7 kilometer as the run. That is the run only if the surface is a globe. So you're assuming a globe, then come up with the conclusion it's a flat Earth. But if your null hypothesis is that it's a flat Earth, you're interrupting.
Yeah,
I don't like interruptions. I don't mind, but you're interrupting.
Yeah,
so if the ground is flat, then you need to obtain a flat Earth formula to compute the distance, which you haven't done yet. I'm done.
So here's the thing. We observe the same angular change in the sky. The Chinese were geocentric flat earthers. They just call it a meter a li. It's all just a ratio when you're using it internally. So using just the observation alone, using it with the coordinate system, is not proof that the Earth is a sphere. You have to externally test it. Otherwise, you're just assuming it. Because here's the thing, like you said, if these 60 nautical mile per degree relationship isn't following, then the Earth isn't a globe. Well, let me show you this real quick. We have the copy link. We have the measurements plotted out for the true positions at the time of occlusion. The blue line is the celestial sphere. The orange dots are, deviations from that at the time of occlusion. They're not following the celestial and terrestrial sphere. Simply looking at a star changing positions doesn't prove the shape of the Earth. It proves the position of the star changes. You can construct a spherical coordinate system to represent that, derive all the same values that have nothing that, and they wouldn't necessarily have to do anything to do with the shape of the Earth. Now, when you transpose that spherical coordinate system onto a plane, you get deviations and whatnot. But what's being but just referencing it internally, you're gonna get what you're saying, like just the change of the position isn't mutually exclusive, and certainly not using a formula that's dependent on a relationship solidified by a fictitious observer. No one's ever been at the center of Earth to observe the true positions of the stars following this relationship. It's a mathematical relationship that's assumed from the way that they behave at higher elevation angles when there's less refraction, as we went over earlier. Now, another part that you said that I want to cover specifically is there that I was going to ask about. Sorry for interrupting you, but I'm curious as to what or how you did for your distance derivation for flat Earth. Because all we have is units of measurement that are a ratio of a coordinate system. No one's disputing that there's going to be an angular change if you were to traverse a distance. So like saying, hey, I need you to come up with a new independent method of getting a measurement. Well, we're using the distance that's internally consistent with the coordinate system. So, and like I said, if you take a chord of that arc length, the difference is 14 centimeters. So I don't know how there's like a different thing that you're trying to assert. I mean, I'll take a look at it, but I don't even know what that means to have. You're saying that you looked at different flat Earth maps, but you've never seen a flat Earth map, but you've computed flat Earth distance. Like, I don't know what you're saying. You have to show me.
Okay. You done? You done?
Yes.
All right. So the chord and the arc length and the chord, those correspond to a sphere, right? You said you looked at the chord. That's a chord of a sphere. So by telling me that you looked at the chord, you're assuming that you're telling me that you assumed a sphere to compute the distance. So thank you. You have been digressing away from the fact that you used a sphere. You said it's a spherical coordinate system, it's an abstract system, and this and that. But by saying that you used the chord, you did confirm that you used a sphere. So let's look at a couple of things. One of them is you just made a statement that looking at stars in the sky does not reveal the shape of the Earth, but that's exactly what celestial theodolite is going to do, right? Or celestial theodolite is asserting that looking at the stars or looking at a star and a peak tells you about the shape of the Earth. So I think you guys should move away from that statement that looking at stars is not going to tell you the shape of the Earth, because that's what you were trying to do. The second one is you showed me that graph of the celestial sphere versus those points, right? You showed me the graph. I was curious to find out what formulas were used. In that graph, I asked you not once, not twice, not thrice, but 7 times on Twitter what formulas they were. You never told me. Even now, you've not told me what formulas they are. You can tell me later on. You don't have to give it to me right now, but you can give them to me in a way that I can read them, because it's going to be hard for me to read.
Yep.
So if you tell me what formula it is, I'm more than happy to work out the relationship and tell you why it's not fitting. If you just show me a graph, then it's hard for me to, or have the formula somewhere where I can go and reference it, right? You don't have to show it to me right now, but you can have it somewhere where I can reference it, or send it to me later. So
we'll
I will comment on that graph once I have the formula. Right.
Yep, fair enough. Okay, well, let me respond to some of that. So, using latitude, longitude, and spherical coordinate systems isn't something that we hide or shy away from. It's our premise. The graticule is a spherical coordinate system defined by positions of the stars. Now, the Earth could be a globe as to why they change positions and whatnot, but that's an untested hypothesis just using and referencing the system with respect to itself. Because it's internally consistent and it's based off of empirical observation. It would be extremely weird if it gave, inconsistent results when it's internally consistent and referencing a ratio for distances that corresponds to the exact change of a celestial body in the sky. Now, the calculator, the Haversine, the formulas, etc., are using a value that is bound to a fictitious observer to tie that spherical coordinate system together. So it is not mutually exclusive. That's an extremely important part of this scenario. Until you have an observer at the center of Earth confirming these angles, then it's just a fictitious coordinate system. It's abstract in that regard. That's what's abstract about it. What's not abstract about it is that it is a spherical coordinate system. That is what the graticule is defined as. Now, the next part that you said is that you can't tell the position of you can't tell the shape of the Earth with respect to just referencing the positions of the bodies alone. The celestial theodolite is not referencing just the position of the bodies themselves. It's referencing a celestial and terrestrial intersection. So these mutually exclusive elevation points at the time of occlusion provide the comparison for when the occlusion should have occurred and which model is closer. So what we went over earlier for how the globe predicts geometric intersections, that is what we're comparing to. So there's nothing wrong with using that, but you have to use another known factor to compare it to. Otherwise, just making the observation alone is assumptive. So it's not the same thing as just saying we see object in sky, therefore we're saying no, we saw an event in the sky that took place that could, where a star was occluded, and there's specific elevation angles involved that are mutually exclusive to both models, which leads to a mutually exclusive outcome. So that's exactly the purpose of this and why it's unique in the sense that it goes beyond just referencing the coordinate system itself for internal consistencies, which I don't think anyone here that's been following the celestial theodolite or any of our work on coordinate systems and all of that would disagree that with that premise. And real quick, and then sorry about the formula thing on Twitter. I didn't see your replies, but basically, if you go into Stellarium and then at the time of occlusion from observer location, you have the angle will be like 2 degrees and whatever 6 arc minutes, true position. If you then just move the observer until that position goes to 90 degrees and then take the distance between that's how we got the ground position difference between them. That's all that's comparing. And then so over this distance, this is what the celestial sphere predicts they would be, and then this is where they were measured at ground distance wise. But yeah, Brian can get you all that he's the one that made that. He can make all that available to you to look at.
Thank you. I'll take a look at it. If you look at a flat plane, if you look at a flat Earth, do you believe the North Pole is at the center of flat Earth?
Yep.
All right. What's the distance from the North Pole to the equator?
Multiply out the latitude lines, it comes out to be like 6210 or something like that. 60 nautical miles per
Right.
latitude
So
line.
60 nautical miles to 69. Sorry. After you. You done?
Yeah, that's it. You got it.
So 60 nautical miles to 69 miles per degree times 90 degrees gives you 6,210 miles from the North Pole to the equator. What is the circumference of the equator on flat Earth?
Well, it's the same because it's just going to be based off of a calculated value. Oh, actually, let me rephrase. We don't know what the circumference is, right? But if you just calculate it based off of positions of the stars and using a symmetrical coordinate system, then it will be
not of the positions of the stars. What is the actual circumference of the equator on flat Earth?
Well, no one's measured that, and no one's measured it on a globe either. It comes from deriving it off of positions of the stars.
It's been measured on the globe using satellites. It's been measured on the globe with lots of different measurements. You guys need to go out and make those measurements on flat Earth. The circumference of the
Can you link me to all the information?
Equator is
that you
known
think you
because the
have
GP of the
about
sun.
measuring the globe with satellites?
Sure, I'm happy to send you those offline, but you can take a look at the rate at which the GP of the sun moves on the equator. You can have two people 69 miles apart on the equinox when the sun is right overhead on the equator. and you can figure out the rate at which the sun moves. Using that, you can work out the circumference of the equator. And that equatorial circumference, if you use that, you will get a North Pole to equator distance of 3959 miles, which is not going to work out for you flat Earth. So the 3959, the North Pole to equator distance, and the 6210 not comport with each other on a flat Earth. So if you try to use a wrong model, then there are going to be contradictions. So for example, if you use Haversine on a flat Earth, there are going to be contradictions. If you try to use the 1 degree per 69 miles and use 6371, which is 3959 miles, there is going to be a contradiction because 1 degree per 69 miles is going to give you 6210, whereas the radius that you've used in your calculation is not 6210, it is 3959. So you see the contradiction there.
No, because nautical miles is just you need to convert nautical miles, the 6210 into 3959. It's not a different number, Brody.
No. Let's do it everything. Let's do everything in terms of miles. So 69 miles per degree times 90 degrees gives you 6210 miles. The radius of the Earth that you used in your calculation is 3959 miles. 3959 is not equal to 6210, right? That's a contradiction. I think you're showing me the result from the recent YouTube video that you posted on your YouTube channel, right?
Yeah, you mentioned just deriving the position, or like the radius value from the angular
Right.
changes.
So this one, this particular video, sorry, up here.
No, that's
right. So this one uses stellarium. This one uses stellarium input to calculate that the sun is 6371 kilometers or 3959 miles above the surface of the Earth, which means measurements of equinox angles that people do are not going to comport. I've made equinox angle measurements that don't agree with that conclusion.
I don't disagree with your equinox. Yeah, I don't disagree with your equinox measurements. There's also an additional problem for, quote unquote problem for flat Earth as well, is that you could take you could take a zenith measurement of the sun, take how long it takes for it to transit its own diameter, and get how big it is, and that comes out to be like 32 miles or 33 miles, something like that. And there's another way you can do it using eclipses as well. I'd have to ask Brian. I can't remember off the top of my head, but that also comes out to a similar value, just giving the what it appears to be based off of the only information you have, its angular size and how fast it's moving at the time. And so with those numbers, like physically, that's way too small to light up the entire Earth and whatnot. So we have different philosophical mechanisms for how the sun works and all that, how it behaves. But just based off of what's seen and the math there derived or therein, what I just posted in main chat there is the equivalence between the two. But none of that is particularly relevant, because what you're trying to say basically is that the flat Earth has a different distance for Pikes Peak. So what is the distance that you think it should be? Like that's the main.
So do you know the formula for distance?
No, can you just
show the formula for distance between 2 points on a flat plane? Let's say you have a flat plane, you've got one point at coordinates x1, x2. So these are linear Cartesian coordinates. Another point at coordinates, one point at coordinates x1, y1, sorry. I always use x1, x2, so I got confused. One point has coordinates x1, y1, second one has coordinates x2, y2. What's the distance between those points on that flat plane? What's the formula?
Yo, my man, just show me the formulas and what the distance should be.
So you can start from that formula. The formula works out to be square root of x1 minus x2 squared plus y1 minus y2 squared. Now your latitudes and longitudes on flat Earth, depending on how you arrange them on your map, typically what I've seen is latitudes radiate out from the North Pole and longitudes are concentric circles around the North Pole. Do you agree with that?
That's not a flat Earth map, bro. That's a different projection of the same spherical coordinate system. If you inputted different
Do you have
distances
a
and got
flat
a
Earth
different,
map on which I can do the
and got,
calculation?
no, there's only the same
Sorry,
thing
after
that
you.
there's only the same thing that everyone's always referencing. It's the same projection under, or it's the same coordinates under a different projection. There's not going to be a different distance, bro. That's crazy.
No, it is crazy that you think the distance is going to be the same regardless of the shape of the Earth. The shape of the Earth is going to dictate the way you compute the distance.
It's
That's
a sphere. Hold on.
plain geometry.
No, I don't disagree, but listen, we are using a spherical coordinate system that changes under different projections, but it represents the same distances. So when you look at it from an AE map, like you just described with concentric outward circles, that's not a different map. That's the same map. If you got a different distance out of that, you did something wrong. Like, for example, you don't draw straight lines on that map, right? You calculate it as an arc or a great circle or whatever it is. I forget the thing.
Why do you
shapes
do
on it.
that? Why do you do that?
Because it's a spherical coordinate system. That's what the graticule is. That's what latitude and longitude is. It doesn't mean that the Earth is a globe.
Because it's a projection of a sphere.
It's a projection of a spherical coordinate system.
It's a projection of a sphere.
Spherical coordinate system.
Here.
You're asserting that it's due to a terrestrial sphere. However, it's based off of just empirical observation, calculating, linearizing the relationship to a fictitious observer. So you don't get to claim mutual exclusivity. You don't get to say, oh, it's de facto a sphere. That's part of my premise, that it's a spherical coordinate system. And then for you to have a different distance improperly using a projection of that coordinate system as a quote unquote flat Earth map is an incorrect use of the thing in which you think defines the sphere. So that's for you to re-examine. Do you want to get any final thoughts off before we wrap up so you can get into your Prezi?
Sure. My final thought would be, if you want to compute a distance, you need a map. I've been asking flat earthers to provide a map. I've not been getting maps. So we make use of the maps that flat earthers appear to use in various calculations, one of them being the Gleason map or the azimuthal projection map. Now that is, I know that that happens to be a projection of a sphere, but if you assume that that is the flat Earth map, then you can work out a certain distance. You need to know the shape of the ground, and you need to know you need to have it mapped in order to work out the distance. If you have the mapping done in terms of coordinates, latitude, longitude, measured in a certain way, you have to have the shape of the ground to figure that out. So that's my final thought on that.
All right. Well, to that, I would say, 1 second here. So an AE map is an azimuthal direction preserving map. Drawing straight lines on it is an improper use of it. I recommend to flat earthers who are using it as a map to read up on how to use it, because you don't draw straight lines on it. Any map that has straight lines drawn on a Gleason's is incorrectly using it. You would never draw a straight line on a Gleason's. So if you use it correctly, the distances are going to be the same, and that's it. So we can, oh, sorry, yours. With that said, thank you for your participation and whatnot. You were extremely cordial. Does anyone else have any questions before we wrap up? Any questions before we wrap?
Oh yeah, you get Jesse muted.
Oh, what's up, Jesse? What do you got?
Hey, Alan. I just had a quick one. Do you believe that it's possible to have 4 fully mutually equidistant points on a flat plane like Haversine says exist on Earth?
Nope, that would only work out on a spherical coordinate system, referencing where they would be at on that coordinate system. I have a question.
Okay,
Does
so
any
it
does
would
anyone
not be
I have a
what?
question. Does anyone have a occlusion where the geometric intersection predicted by the globe matched what the globe predicted, or was it always pretty much off by Earth curvature? Does anyone have any of those? So before we get into hypotheticals of using the coordinate system and what relates to it when you internally reference it, right? You get guys, guess what? Spoiler alert, you get spherical results because it's a spherical coordinate system. We're externally testing said internally consistent coordinate system and the use there of it. And none of these measurements show that the Earth is actually a sphere. It shows that the curvature comes from the sky instead. Otherwise, these errors would all be reversed. How come when I show it lining up geometrically for the globe, it shows it as if it puts the Earth curvature difference for that's how much flat Earth is off. But in reality, when we go to any measurement, the globe is off by what they predict as curvature every time for intersections. Does anyone have any measurements of that? Or do we want to keep referencing hey, how about this? How about we take 3 points and add up their ASIEs and see if it makes a spherical excess triangle? Anyone want to do that? We could just
Definitely. Bacon did it.
we could just reference the coordinate system itself. That's just referencing the coordinate system itself. Of course, it's going to come out with excess. That's our premise, guys. Come on. Are there any
But
actual
that raises
questions?
a big question because
Go ahead.
You know what? At the moment in time,
you know what also raises a big question, Jesse? That none of these measurements corresponded to what the globe geometrically predicts. Isn't that crazy? Isn't that fucking wild?
Well, according to you, because you're using a method of what the globe predicts that's invalid. No glober supports it. So that's just a straw man. It actually does match what the globe predicts based on just simple geometry. But as to the azimuths...
Actually, real quick here.
If
you say that it's a straw man, but what we went over earlier and the last time we spoke, the French using geometric intersections, comparing true position, eclipse predictions, all geocentric ephemeris, comparing geocentric positions for the intersections, comparing it to where a fictitious observer would be on this or in the center of Earth with the Baselian elements for all their alignments. Same thing for conjunctions. Everything that the globe references, if you want to know when the sun's going to set, you need to know when it's going to geometrically be occluded by the celestial horizon, when it's going to start getting into negative coordinates for there to be a 35 arc minute of refraction to apply to it to keep it up lingering. So when you say that like no glober agrees with it, I don't need people on Discord to agree with me to form a consensus. I don't get my authority from that. I have primary sources of astronomy textbooks that all agree with me. I have data from NASA predicting eclipses and saying how they do it, all showing geometric intersections. I don't need people on Discord to go, oh yeah, you're right.
You mentioned your primary sources of astronomy textbooks. Sorry, Jesse, do you want to go ahead?
I just wanted to say that the French were actually correcting they were making real world observations which they recognized to be refracted, and then they were correcting for refraction to translate that to the geometric. And that's not what premise. You're doing.
Hold on a second. That's exactly what they did, and that's exactly what we're doing. When we look at the observer location and the occlusion, and we look at where the star was for the observer, that's what the globe predicts where the star should be for the observer. That's exactly what we're doing. That's exactly the method. And then we do the same thing from the peak position.
You've got
atmosphere
turned off. Except you've got atmosphere turned off, which means you're assuming that there's no refraction at play.
Jesse, what you just said is absolutely absurd. Refraction turned off is how you get the difference between the apparent position and where the true position is. Obviously, that's subtracting refraction. If you go into Stellarium Pike's Peak right now, you're going to get 13 arc minutes of refraction. That's the value that we have here. You get that by subtracting true position from apparent. So when you say that you're not doing that and then describe exactly the way to determine that, that's crazy. Like, what do you think you just said when you said you're not comparing the geometric intersections, and then you look at this spreadsheet and it's all about comparing geometric intersections? And you just confirmed for us all that the French were also doing that. So we're doing the exact same thing. And then you said by turning refraction off, we're assuming what? Like, what you're saying doesn't even make sense.
But do you
What do
see
you,
that 169 in H12?
Jesse, what do you think is different about
No,
what
I'm right.
what do you think is different about what we're comparing with geometric intersections? We have the true position relative to the peak, true position relative to the observer. This intersection difference right here is the true position of the star for the observer minus the geometric elevation of the peak. What are we doing? You said that we were
Is it?
doing something.
Let me.
You hold on, real quick. You said that we're doing something different than what the French were doing. How?
Well, let me ask a clarifying question.
Let me
Is it your
ask it.
claim?
Hold on a second, Jesse. Let me ask a clarifying question because you just asserted that we were doing a completely different thing while citing the exact same thing that we're doing and pretending it's a different thing. So can you just go, hey, I misspoke? You are doing
I don't
geometric
believe I did, but
intersections
I want to ask a
comparisons.
question to find out.
So real quick, before you ask your question, this whole time when we talk about geometric intersections for all these months, you're now saying that you're unsure that that's what we're doing. Is that your position?
I'm quite sure I know what you're doing, but I'm going to give you the benefit of the doubt and ask to confirm if I may. But
Continue.
if you're not allowing me, just say so. Is it true that you're claiming that at the moment that the occlusion is observed, that the observer, the mountain peak, and the star are in a geometrically straight line with each other? Is that your claim?
At the time of occlusion, is the star geometrically aligned with the peak and then peak to the observer, right? That was your question?
Almost. It was almost my question. I said at the moment that the occlusion is observed, I'm talking about the moment it's observed at. Are you claiming that at that moment that the observer, the peak, and the star are in a geometrically straight line?
Yes, that's what causes the occlusion.
Okay, the French were not claiming that. They recognized that at the moment that the occlusion was observed, the star and the peak and the observer were not in a geometrically straight line, which is why they then performed an addition or subtraction for refraction. And that's what
Yeah,
you're not doing. You're
Jesse,
assuming something different than they did
Jesse,
and not correcting.
that's exactly what we're doing for the globe. That's insane. We're literally
But
doing the
is
same
it
thing.
true that
It would be true if the Earth is flat. If the Earth isn't flat, then when you add the angle back or when you add the arc length back, it wouldn't be true. So when they would go
well,
to
that was the beginning
compare,
of my next question.
so when they go to compare, it would be different. That's what we show with when we look at the true or when we look at what it would look like if it aligned up with the globe. We get this where it changes it. So now we have the difference, and now the true position of the star would only be 244. It would be literally off by the half central angle in elevation over that arc length. That's how it would affect the measurements. If the Earth were globe, they would be reversed, but it's completely the opposite. And then whatever refraction is left, you guys cut off and just say, oh, well, it's just close enough, the apparent position, blah, blah, blah. But that's not, the apparent position doesn't define anything about the globe. The globe is defined by geometric positions. That's what relates to geographic positions. That's what makes eclipse predictions, occultations, and conjunctions. So what the French did,
Except the French,
what the French did,
they,
right? If you're an observer and you see the occlusion and you subtract how much refraction there is at that angle, this is exactly what you're going to get. If it, let's say Mike is a Frenchman, right? And Pikes Peak is in France or whatever, right? So he's looking out, he sees this occlusion, he thinks the Earth's a globe, right? So he thinks that the mountain elevation is 217. He gets the occlusion. He references his handy Settleman or GG Bennett formula. He's like, oh, there's about 13 minutes of refraction. Okay. At the time of occlusion, right? He subtracts that amount. He gets 206. That's exactly what the French did. That's why when it's at a higher angle, they didn't account for refraction because the differences are about the same. Like, there's not much difference between the two. So when we're comparing where the true position was with respect to the object occluding it, that's exactly this is the exact outcome that would have occurred when the French did it. There's no difference.
Well, is it true that the French recorded the time of occlusion over something closer like a building roof or something, and then assumed that was the refracted position, and then subtracted astronomic refraction to get the true geometric position? Is that true? Yes, there it is. They assumed that the star was not in its geometric.
My mic was off. Yeah, when the star gets occluded at a high zenith angle, they're assuming that the difference between the refracted position and the true position is basically nothing. So the reference to the apparent as the true is negligible. Now, when they have buddy, we're getting there. When you get to a lower, you have refraction that has to be accounted for. So you're going to subtract that out at the time of occlusion to get the true position of the star.
So this is my question to you.
Mm-hmm.
If the French believed that at the moment of occlusion, the observer, the peak, and the star were in a geometrically straight line, then why did they have to subtract refraction to get the true? If they already had the true position, why did they have to subtract refraction to get the true position?
It's the difference between sidereal and local mean time.
Well,
so did they or did they not have the true position at the moment the occlusion was observed for them?
The true position is
they had to subtract out.
reference.
They had to subtract out refraction. That's exactly what we're doing. We have an occlusion. We have a drop over distance. We subtract out the refraction to reference where the star was at the time of occlusion.
Well, they didn't have stellarium, so they were starting with the
all you would have to do is add the arc length back.
So right, and that's what you're not doing. So
that's
if
exactly,
you're starting,
buddy. Hold on a second, Jesse.
What are you talking about?
You add the arc length back for the flat Earth comparison to compare from the location that did the occluding. You don't do that for the globe. The globe is observer centric predictions. But
see that 169. You are comparing that to the real world angle and timing of the star.
No shit.
Duh.
And you're not correcting for refraction like the French were. They were obviously doing it in the reverse order. They were starting with the apparent position and correcting for refraction to get the true position. You're starting with the true position from stellarium and then treating that as the apparent position by ignoring refraction. That's the difference between what you're doing and what they're doing. If it's true that they believe, I'm almost done. If it's true that they believed that the apparent or that the angle to the star was the geometric angle at the moment that the occlusion was observed, then they would not have had to subtract refraction.
They wouldn't think that, bro. They think that they lived on a globe. Like, I don't disagree that like the geometric implication for what we're doing is star peak to observer as a true geometric angle. That's not what I'm saying. Like, on a globe, it would be different. I prefaced my answer to you that my alignment would only be if the Earth is flat. If the Earth is a globe, there would be an earlier alignment with respect to the observer prediction, but it would still align, but it would be an observer centric prediction. It wouldn't be a prediction from at the object doing the occlusion, because we were adding the arc length back to compare the elevation differences at the time of occlusion. So that's the difference there. What we're doing isn't strawmanning the globe. It's comparing the geometric intersections, just the raw geometric intersections. Which one's going to be closer? That's it. So saying that the French did this and you're doing that, we're all doing the same thing. We're all referencing the star's geocentric position at the time of occlusion. Is that what the French were doing? Because that's what I'm doing.
It's not what the French were doing.
Oh,
They were accounting for refraction. That's why they subtracted refraction. And if you added refraction to your geometric prediction from stellarium, then it would match the globe within standard
no,
refraction. They were
no.
using something closer, so they didn't have to worry about standard refraction.
It would be off by 2 arc minutes for the geometric intersection. Like we went through this heavily last week for every measurement. None of it ends up with a geometric occlusion for what the globe predicts. They end up almost always being above it at the time of occlusion. There's no consistency. There's no consistency to the amount that the gamma between us is off by versus the amount of predicted refraction. In every scenario, you have to cut the refraction amount short to just say that it matches the flat Earth angle when we add the arc length back. That's retarded. And saying that what the French did and what we're doing is different and we're not blah, 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 accounting for refraction. They're referencing the true position of the star. We're referencing the true position of the star also relative to the observer. That's it. That's all they needed to do. Yeah. We could read it right here, buddy. When the reason that they didn't account for refraction at higher angles is because the difference between the true position and the apparent position is negligible. So they're treating it as true. When they say that they have, where's my freaking thing? When they say that they have to account for it, they're talking about subtracting it out to get the true position. So we need to know where that true position's at. Jesse, do we know where the true position's at for the observer? Is it 206 at the time of occlusion? Yay or nay?
That's the geometric position, but that's not
correct.
What's going to
correct. And what we're predicting,
but that's
here,
not going to comport with the occlusion time, according to the French. They did not believe that. By the way, I need to respond to something you said. If I'm
hang on a second, you're saying a lot of stuff about what you think the French believe. I'm going to need primary source documents because all either of us have for what the French did is this reference right here. So to add on and supplement and hypothesize, I'm going to need to see some primary sources. Otherwise, the argument is confined to these instructions here.
Well, I think you agreed that they believed that at the time of occlusion being observed, the star was not at its geometric angle was not in a straight line between the observer and the peak. They did not agree with you on that, right?
Correct. And I wouldn't I wouldn't impose that on them. That's why I specifically prefaced my answer to you with that's only true on flat Earth.
Right. So they were not doing the same thing you're doing. But I did have something I needed to respond to, if I may.
Go ahead.
You said that if refraction correction were added to star observer true, that it would still not be closer to the globe prediction. The fact is, almost all of them would be if you simply subtract astronomic refraction and add terrestrial standard refraction, then almost all of them are closer to the globe prediction.
Come again?
If you take the star observer true angle from stellarium, subtract astronomic refraction,
it's already been
add in.
It's already, hold on. Astronomic refraction is already removed at the true position. So like, what does that mean? You want me to subtract it again? Like if I add 2 arc minutes of refraction to this, it becomes 208. It doesn't help at all. I don't understand what you're saying.
Well, what I'm saying is if you correct for the 2 refractions, then it matches the globe prediction almost every time.
Tell me what formula to enter in here.
Okay, let's see. Let me find my bearings. It's your spreadsheet, and I'm not as familiar with it as Mine? Okay, so we have. All right, add. So take the angle from star observer true, or you could just start with star observer apparent.
Star obs
So okay,
true.
so add in terrestrial, or add in astronomic refraction.
Do you want me to use the apparent position or not? Are we subtracting it or adding it?
I believe adding it. I mean, I did not prepare for this.
Do you want you want me to add refraction back and then add terrestrial refraction on top of it? Is that what you're saying?
Add astronomic refraction, subtracts terrestrial refraction. Yes. So parenthesize that and put and subtract or add astronomic refraction to it.
Gotcha. Okay. Do I not have a? No, that's what is that? B16, and then minus terrestrial, or no? What'd you say? Plus.
And then put parentheses around. Put parentheses around that just so we know it's grouped, right?
Mm-hmm.
And then from that, subtract terrestrial refraction, standard terrestrial refraction.
Oh, I had a variable for that setup. K11. Circular dependency didn't work. We did something wrong. K11. Oh, whoops. I know why. That's the wrong value. Need K17. There we go. We get 2.
To what? Degrees?
I would say arc minutes probably.
Must be, yeah.
Hang on. Let me convert.
Well, the observer true was 2 degrees and 10, or 2.1.
Yeah,
okay.
Yeah, it comes out to that 219.
Okay. Now feed that into tangent times the distance and see what we get.
Yeah, Jesse, I've done all of this. This is all right here.
So you're,
and Jesse, this is all right here in the apparent intersections. It gets closer for this one, but it's inconsistent with other ones. So for this one, they end up being, even with the refracted peak, they're still above it by 1 arc minute. And
how many arc minutes off is flat Earth?
27.
5? 20. What's that?
Yeah, 5 arc minutes. Oh, I'm sorry, I was thinking of time. Yeah, it comes out to be 27 arc minutes, or real seconds, rather. But yeah.
Right. So if you go through this, you'll find that the globe now matches closer than the flat Earth does for most of them. And the ones where the flat Earth is closer.
Jesse, nobody's saying, number one, that you can't add 2 different corrections to make it closer. Okay. The premise is just raw geometric intersections. And if the globe was supported by any of that, then the refraction value differences would be closer to actually, what's observed. So like this number up here where we have the astronomical refraction for their intersection, this wasn't what was observed, right? This means that the star would still be almost 3 arc minutes above the peak at the time of occlusion for the apparent. Now, if there was no mountain here, everyone that's a globe lad would be happy to say, oh yeah, of course there's 17 arc minutes of refraction here. But there wasn't. There never is the amount.
How do you know? How do you know?
Because there was an occlusion that occurred, and that value means that it would still be above it. It would have taken longer to set. It would have lingered on the peak. And although you don't accept the apparent apparent images not causing an occlusion, like that's why I don't consider that at all and just go off the geometrics. But even considering that, it's still off. It would still be a minute above it. There's no room for the refraction amount differences. There's only an occlusion that occurs when a star traverses that arc length, and at the other end of it, it gets occluded. And it just so happens that it just so happens that every single time that the raw geometric intersections are close, or what flat Earth predicts, and the refraction amount has to be, up to two types of corrections are added to make it equivalent. That's not our hypothesis. That's a separate hypothesis that maybe you can do like a presentation on or whatever. But all of the stuff that you're requesting is included in here, and it's not consistent with predicting an occlusion. It's not the cause of the occlusion, right? When the sun's setting, the cause of it is it's being geometrically occluded by the curvature of Earth, right? Its celestial coordinates become negative because it's below the celestial horizon, which means that it's below the equator relative to the observer and how they see the sky. So it's being geometrically occluded by Earth. This is what defines the baseline for all occlusion predictions. So we're predicting it closer every single time with no additional corrections. We couldn't care less about how many. Do you want to add a third one? You want to make it real close? I'll give you a third one. You want a third one? Like none of that matters at all. Because all you're saying is that if I add two additional corrections, I can make it, I can explain why the Earth is appearing flat in all these measurements. That sounds like a different hypothesis.
So, but don't you find it interesting that if we consider the globe model and correct for the claimed lifting of the star and the mountain according to astronomic and standard refraction, that we do get an angle that is almost always closer to the predicted geometric globe angle?
No, because what's measured isn't that amount of refraction. So if there was no peak there, you guys would just say, oh yeah, that's how much refraction is needed to make it appear that high. But then when there's a peak there, you're like, oh, it's actually, I guess it was actually lower, I guess. That's insane. Well, I guess there wasn't that much refraction. That's a complete contradiction to the backbone of the model to make it appear that it's flat. Like, do you think it's interesting that if you cut off how much refraction there's predicted to be, you can make it equivalent to what we just raw dog predict with rise over run? Maybe that's an interesting thing that you should look into. So when we look at geometric intersections here, you guys end up being including the refracted position off by 30 arc seconds, which is half of an arc minute there. So it's three real seconds of lingering above the thing. If you consider geometric intersections, you're 2 arc minutes off. As we continue, we got Blue Mountain here, 22 arc seconds. That's a lot closer for the geometric, or for the two apparents, but for the geometric intersections, still off by 2. So you're cutting off the 18 to make it 17 so that you could explain why this is a flat Earth measurement. Don't care about the secondary corrections when we're over here rise over running to the peak and doing geometric comparisons. Here we have Mount Rosa again, so 2 arc minutes above the peak, a little closer on that one for the geometric when you add the terrestrial, because it comes out, what was that, 24 arc seconds, so it is closer on that. But again, these are just comparing situations where when it's over the peak, no one's like, oh dang, it didn't delay the occlusion at all. Like whenever it's like close enough, you guys are like, oh yeah, nailed it, totally closer. That's inconsistent and not, that's a secondary thing that like if we added corrections, you think we could just make it closer to? Yeah, obviously. So here we have Green Mountain, 4 arc minutes above the peak at the time of occlusion, easily measurable with celestial theodolite. Using the refracted position of the peak, you're still 2 arc minutes above it. So still 14 seconds in delay of occlusion. None of these are quote unquote closer. They're measurements that didn't occur because of the amount of predicted refraction. You're looking at it with rose tinted glasses or whatever. Because none of these are actually what was measured in terms of how much refraction there would have had to have been there to explain why the star is at that angle without refraction. North Peak, 3 arc minutes above the peak at the time of occlusion. Adding refraction to it for terrestrial, you're 2 arc minutes and two arc seconds above the peak still. So instead of 3, you're 2 arc minutes off. Still above the peak. That doesn't lead to an occlusion. In the same way that when the sun intersects with the celestial horizon, you guys are like, oh, it's just refracted up by however much it needs to be in every scenario. Getaway Mountain, 2 arc minutes intersection difference for the geometric, 13 arc seconds for the apparent, so is closer on that one. but again, inconsistent with the geometric in other ones where it was still above at the time of occlusion. But look, it's closer. Let's take that one or whatever, and ignore all the other ones where it should have been geometrically above it if refraction is a mechanism as told to us by the globe lads, where it lifts up objects around objects that are physically occluding them. So here we have houndstooth. You guys predict to be 1 arc minute still above, and then using terrestrial refraction at the time, because there wasn't a lot, it's only an arc second, you end up being still off by basically the same amount. But it's closer, but it didn't happen. It didn't change the timing in reality to make it shift to where the air differences would be the refraction amount for us. So it didn't have anything to do with it. Let's keep going. We got a couple more to get through. Might as well run them all again. Blend Mountain, same scenario. We have this one's for an emergence, so it's reversed. Now, so it would have emerged 2 arc minutes earlier because it would have been above the geometric peak, and then that means it would have emerged 13 seconds, 13 real seconds sooner. Didn't happen. Considering the geometric considering the refracted position of the peak, it would have occurred 7 seconds earlier instead of 13, because it's 1 arc minute of elevation differences. Didn't happen until true position was aligned with the whatever was at the other end of that arc length. The same in every single measurement, which is what causes this air difference where we're off by 12, you guys are off by double the amount.
Oh, I don't. What was your approximate margin of uncertainty just for the method in general? 2 arc minutes, 4 arc minutes, plus or minus?
Good question. Let me see. Do I have? Let's see. Celestial Theodolite, air bars, intersections. So this is distance. This is elevation. This is where's my? Hold on a second. I do have intersection air bars, but let's see. This is distance. This is elevation.
I can convert an angle from a distance and a vertical distance.
Yeah, hold on one second. Where are my intersection ones? 1 second. I may not have those. I might have to make some. I could have sworn I had intersection differences on the air bars.
I think I calculated once and I got a standard deviation of like plus or minus 4 arc seconds or something.
That sounds reasonable. Did you do like a normal Gauss or whatever, Gaussian normal distribution?
No, I just did a standard deviation on like say a bunch of Pikes Peaks ones. So it's like, the source data is kind of all the same, but the only variable is just the random noise.
Yeah, I will go through for next week and have air bars for that with a normal Gaussian distribution like I have for distances and elevations.
Cool.
I thought I had those. I apologize.
Oh, that's okay. So how many of the data points are actually outside of, say, a 5 arc minute or 4 arc minute margin of uncertainty when using the formula that you put in for me with the atmospheric and astronomic refraction correction?
Well, you said arc second earlier. Is it arc seconds or arc minutes?
Arc minutes.
I don't know. I haven't done a standard dev.
No, I mean, if we just go through your spreadsheet and compare that green cell you put in L11 to, let's see, oh, G12, I guess, right? Is that Yeah, the globe predicted. Yeah. So it looks like 7, 8, 9, couple of arc minutes there.
Yeah, but
Put a
again,
delta.
this is an exercise in comparing a position after it's been corrected for, not showing
Which is
the amount that was actually measured at the occlusion. So if you were to add how much refraction you're trying to co-opt instead of the amount that was predicted, you wouldn't even get that amount. So again, this is an exercise, for you to do or something, because like we don't care about the apparent
I did it.
positions at all.
Well, this doesn't have anything to do with the apparent positions. This translates the geometric position of the star to the geometric position of the mountain. That's
The
you add the we
so
added the
so one second.
astronomical
One
refraction.
sec. One second. Earlier, you said it has everything to do with refraction because you had me add it into the true position of the star for the observer, and then subtract out terrestrial refraction for some reason.
Because the mountain is also displaced. And so in the globe, according to the globe model, the mainstream globe model that's been in use for thousands of years, or at least hundreds of years, the difference in geometric angle between a star and a mountain is the difference between astronomic and terrestrial refraction. So, and I'm not asking you to agree with the globe model. Obviously, you don't. But this is the globe model. And I want to know how many of these data points actually are outside of the margin of uncertainty as far as matching the globe prediction using the correct globe model that you have in that green cell on L11.
Well, again, we're not using an incorrect globe model. You're correcting from a baseline of where the intersection was missed. So that's a complete contextual rephrasing of it to make it appear like we're doing something incorrect when we went over, like, I'm not going to argue this endlessly with you. We just went over all the scenarios where they're using geometric intersections to define when an event should occur. Adding refraction after the fact is a secondary hypothesis. In every scenario, you're off on the geometric predictions. I don't care if you add refraction back in and want to do an analysis from that way. That's a separate thing, and I've included all of that the best I could with so far for the comparison, although I don't consider it because it has nothing to do, like, the apparent position of a body isn't actually what defines its geographic position. You're going to need to subtract out the refraction to get the geocentric position of it for it to have any physical meaning to the graticule. So I don't care that the apparent position may optically be closer to what is measured just using optics. Means that we're doing
All right.
physical intersections because that's the cause of the event. When the sun sets, right, it's because it's being geometrically occluded by the curvature of Earth, right, relative to the observer. It's going below the horizon on the celestial. Its celestial coordinates become negative. That's what starts the event, and then deviations from that are refracted. Well, we have an occlusion here. That when's this event's going to start? Is it going to start when the globe intersects, or is it going to be with respect to a flat Earth? Because if we compare the position to the fictitious observer, where they say the star's true position is for the globe, which is what the globe predicts, which is what you're going to add refraction to change the position, but have no causal relation to the actual occlusion. But this is what the difference is. And then for flat Earth, the difference is 2. These two numbers are the driving factor between the arc length and the curvature relationship, the curvature of that arc length relationship. None of these refraction apparent position values correspond to anything geometrically in relation to the coordinate system. Those are all after the fact things to try and explain it. So I'm not interested in any of that.
All right. Well, thank you very much, Alan. I had one more question about the gradicle you keep mentioning. Do you believe there is any way possible to draw any kind of coordinate system? I don't care what kind of shape of lines for your axis lines, but any kind of coordinate system to draw it on a flat plane where Haversine would then work between any 2 points on that flat plane using that coordinate system grid you've drawn on there. But do you believe that's possible or impossible?
Well, if you take a spherical coordinate system and project it on a flat plane, you're going to have to make corrections to it the same way that you do when you take a globe, you take the spherical coordinate system that is represented in the globe projection. If you take that same projection and put that on an AE map, you have to use the corresponding corrections for it to like describe the distances and like how it's going to be between that. So when you say, is there a way that we could make it work on a flat Earth? Well, depending on how you're
Yeah,
using
physically flat.
depending on how you're using the projection, there would just be some corresponding correction to it because that's all that's being transferred is information from the spherical coordinate system to another plane. So that's
But
not I don't
so you think there's some way I could draw the right curves of lines and have the right numbers written by those lines and form a grid on a flat plane where I could use Habersign between any 2 points on that grid with its coordinates, and it would give me the actual physical straight line distance between those 2 points as measured with a ruler?
if you do the proper corresponding corrections and plot it out correctly, because that's the same thing that happens on an AE map. Is what people will do is they'll draw straight lines across an AE map and be like, "Oh, look, it's different" or whatever. But the northern hemisphere and the southern hemisphere are represented by the same latitude and longitude lines. They're just straightened out for the projection. They all represent the same distance. It's not a different distance unit. So you have to use it within the coordinate system in which it's being projected in. So you probably could do it if you applied corresponding corrections.
All right, well, thank you. That is a huge claim, and if you could prove that, it would be absolutely amazing for flat Earth. Thank you.
No problem. Hey, you know what would be great for the globe? If any of the geometric intersections that are described by the use of the coordinate system corresponded to the occlusion geometry instead of corresponding to what a flat Earth would predict. That'd be super dope too. Instead of just like hypothetically plotting out points on a coordinate system and then asking if you project it into a different form, could you still maintain the geometry of it? Possibly. Don't know, don't care. If you have a mountain peak that's a certain elevation on a flat Earth versus a globe, and there's an event that's going to be an occlusion, which when would you predict is closer in elevation for the predictions? You probably go with the globe, right? Because you think the Earth's a globe. But it turns out all those geometric intersection differences are off by literally what's predicted as drop over distance of that arc length. So, if you want to get any final thoughts out, we can wrap up. Otherwise, we can do like one or two more questions if they're quick ones from other people. But if not, I'm going to go ahead and wrap, and then Earthly Skeptic is going to get to his prezi. He's been patiently awaiting.
Thank you, Alan. I really appreciate it.
I mildly appreciate this too. It's been very pleasant. Thank you, Jesse.
You're very gracious.
All right. Let us, if there are no further questions, lads, we can wrap for the night. And let's see here. I think we're good. Coco, thank you very much for segueing us into all of that. Earthly Skeptic, thank you for also participating and going through that. And it was a lot more meaningful to go through it with someone who understands the core of it, more readily. So that was awesome for you to step in there when you did. So thank you for that. Good luck with your presentation, sir.
Thank you.
I will get you a written response or whatever for the following week, and have a good night. Gio, thanks again for hosting. Much
Thank you,
appreciated.
Alan.
Mm-hmm. Hey guys, it's me, Gio. I'm not at the mic, but no problem, Alan. You're awesome. Oh, dude, you're making me blush. But thank you.
You
You
go,
gotta mention
Alan.
you gotta mention the mushrooms, and then we'll believe you.
Thank you, Alan.
All right, so the LeBron of presentation stands true, unrefuted, stands strong, undefeated. See you next week.
And there's a touch